So this week we're going to start talking about all this moisture and creating clouds and creating precipitation. There's a method we use to view precipitation, and you all have seen it probably on your local TV and all. It's local radar. Radar is great. All it does is send a little pulse out, which reflects off of things like precipitation, and eventually comes back and received. That information then is received by the radar. How strong that pulse is sent back is how heavy the precipitation might be, or maybe even ice. Big crystals of ice can precipitate. And this is a view of the current radar here in New York City area. Lots and lots of heavy rain. You can actually see a band right here going through that area. And if we loop that, you can actually see the motion of it and all, and how the precipitation is moving with time. So, what I really wanted to show was, with this, there are different products that the Weather Service has available. And one of those is velocity. So say I take a velocity data, and it will come up here in a minute, and we'll see actual motion of the little individual particles within it. So what you're seeing here is velocity of these precipitation particles. And with that, you can actually see where they're moving. In other words, right now there's a nice strong southeast wind there, and that is the direction of motion. And that is shown here by moving away from the radar in this direction. And this is the strength, the speed of that as well. So there's other parts of radar. So we have dual pole now, which is available. So we've always, for many years, just had one radar beam going out, and you could see what it reflected back. Well, now we actually have the radar pulse going in two directions. There's a vertical and a horizontal. So what you're seeing is actually how the precipitation looks in two dimensions, not just a one-dimensional, oh, there's a particle. So with that in mind, let's take a look at what that means here for just a little bit. There's what we call correlation coefficient, a CC. What that is it looks around and sees the shape that it has at 1 pixel. It compares that to the pixels around it. If they're all similar in size, the correlation coefficient is very high, like 99%. That happens a lot in snow and rain. However, notice here, it's way off. What that indicates is there's a change in the shape in this area. That change in shape is actually hail. Hail doesn't look like any other raindrop or snowflake. It has a different shape. So now you're seeing it in real time right here. One of the beautiful things about the radar being in dual pole is I can pick out a hail column inside that radar envelope and be able to forecast maybe even when it's going to hit the ground. And the more pronounced it is, maybe the bigger that hail might be, I can get an estimate on. And here you can even see some other ways of looking at it and different other things as well. There's another aspect to this as well that can be used. This is in tornado forecasting. This example, I have a tornado. I talked about wind velocities here a minute ago. Well, take a look. We have wind moving in one direction here and one direction here, and they're right next to each other. And notice how bright the collars are. These are very strong winds, probably over 100 miles an hour in each direction. This is a hook echo. It's shaped like a hook, and that is where a tornado likes to form. So dual pole with that then gives me an option of looking at that correlation coefficient. If I look at the correlation coefficient, here's where the tornado might be occurring. Whoa, what is this? This is very different than everything around it. What it is seeing is debris. And looking at it, another elevation up, I'm still seeing debris. So debris is being pulled up into that tornado. So now I have evidence that the tornado has hit the ground and is producing debris. So in this case, I have literally verified a tornado on the ground using Doppler radar. Many instances, I'm not going to be able to see the debris as well. But when I can like this, I can come out with a pretty confident warning to somebody that we have a tornado. So let's talk a little bit about all this wonderful moisture and all now, and what we can do to make clouds. Guess what? They're not as easy as you would think. So, with that, how do clouds and precipitation form? Well, we know water vapor is invisible, and we know clouds we can see. So there must be something that causes a cloud to form. Well, let's compare droplet sizes first. Look at the raindrop. This is about a comparison of the actual, the sizes aren't this big. Obviously, a raindrop's much smaller, but this relationship between the two is similar. Cloud droplets are very, very tiny. So that complicates things, of course. As you may have been learning in meteorology, nothing's ever nice and simple. If you have a nice flat surface, when we say that relative humidity reaches 100%, we're saying yes, there's evaporation and condensation occurring at exactly the same rate. Unfortunately, on a curved surface, saturation's a little more complicated. Because of a curved surface, it's easy for water to actually go back into a vapor. Much easier than on a flat surface. So the stronger that curve is, the quicker water vapor can evaporate. So if we didn't have anything else out there impacting it, you would literally need 300 to 400% relative humidity to form a cloud droplet because they're so tiny. However, something comes into play. It's called cloud condensation nuclei. What are they? Well, they can be anything from sea salt to certain types of dust, maybe pollen in the air. And so at different parts of where you're located in the United States or any other country, you have different cloud condensation nuclei. What it does, it forms a solution in that little tiny water droplet that we just saw. And instead of allowing it to go right back out and evaporate, it says, no, I'm not going to let you. So it just holds it there. That is what allows raindrops, or in this case, cloud droplets, to form. So we actually do get cloud forming right around 100% or slightly below of your con. So now there's another aspect to it. Guess what? These cloud droplets, because they're so tiny, they don't freeze very easily. So if you were to lower the temperature down, way, way down, you could freeze them. But instead, at 32 degrees, or even 31 or 30, almost all that is very, very, very cold liquid in those clouds. So what freezes them? Ice nuclei. It's similar, not quite the same as cloud condensation nuclei. But when it gets onto a surface of water, it allows them to freeze. And typically, it's most active around -9 Celsius. So when you're looking into a cloud, and if you see these nice little vapory clouds out there, you know the temperature is probably at least 16 Fahrenheit, -9 Celsius, in that range. So now we've gone from forming a little cloud droplet to forming an ice crystal. So with that, precipitation. Well, those ice crystals and cloud droplets don't drop to the ground, right? They're the flow of air upwards, holding them up. Friction is going to keep it from dropping very fast. So there are different things that keep that little droplets up in the atmosphere. As they get bigger, they begin to fall, and they'll reach a certain velocity because of friction. that's regulated by gravity and the resistance to air. So they're moving at a constant velocity. We're going to talk a whole lot more about those kind of things in the next chapter. So how does these big enough droplets form? Well, there's two processes. There's collision coalescence and a Bergeron-Findyson effect. So we're going to start with collision coalescence. So here, the cloud temperatures are basically greater than 0 Celsius. There's no ice involved in this. What you get is a droplet bumped into another droplet, bumped into another droplet, and all of a sudden, it gets bigger. Now it's starting to suck up more droplets and eventually becomes big enough to fall faster, reach a terminal velocity, and be a raindrop. This can occur in the summertime, particularly, or very warm conditions. We don't get a lot of this in the northern, up in our latitude that often. We get it in the summer. Bergeron-Findyson effect, however, is the way most precipitation develops in the United States. So what does that mean? Well, what it means is we have ice that forms in the cloud. We said we have ice condensation nuclei, ice crystalline nuclei. When the first droplet switches from a droplet to an ice particle, little crystal. Remember we learned in the last chapter that saturation vapor pressure is greater over a water droplet than over an ice crystal. Not by a lot, but it is greater. So what happens is all these water droplets, all the water vapor is flowing away from them and towards these ice crystals. So what happens is the ice crystals grow, the water droplets go away. So you wind up with all ice in the cloud. And those ice crystals have grown in size. They become snowflakes and begin to fall. And that is how you get most of our precipitation. Yes, it melts on the way down. But they become, first, almost all precipitation in the United States forms as snow in the clouds. One of the things you can get with clouds as well is if the air is dry enough down below them, all the rain will evaporate as it's coming out, and you get virga. There are different kinds of precipitation. Rain is what falls as a liquid. Drizzle is, I've been getting too much of that this week. Very tiny raindrops. Just kind of makes everything just a little damp and not necessarily real wet. Oh yeah, there's snow, which are ice crystals. And there are different shapes to these ice crystals. What I want to hypothesize to you is how difficult it is to forecast snow depth. Ice crystals can be dendrites, which are big, fluffy flakes. Most of the time they are. However, they can also be pallets, columns, even tinier dendrites. So, look at the size difference. So if I said I am going to have 5 inches of snow, I know how much precipitation, how much total liquid is going to fall out of that cloud. Now I've got to also figure out which one of these shapes is that snow going to be. And depending on which shape, that 5 inches could become 7 or 8, or maybe 2 or 3. It all depends on the shape, and we work really hard to try to figure out what the most likely shape will be for your snowfall. And here you can see what typically happens as the snow is dropping out of your cloud from the Bergeron-Findyson effect. It's going to reach warmer air. Normally, most of the air below it after a certain altitude is all above freezing. The snow is going to melt. Believe it or not, it only takes about 1,000 feet of temperatures above freezing to melt snow. Doesn't take a lot. So typically, everything will become rain. However, say that little area of warmth is relatively small and all. Well, and yet below there, it's back below freezing. What happens is the precipitation, snow melts to rain, and when it hits the ground, however, the temperature has dropped back below freezing. In the very lowest part of the atmosphere, we get ice. So you get freezing rain. If it's a bigger column that can freeze, you might get sleet. And if you don't go below freezing at all, or just a little tiny bit, maybe it's all snow that's falling. So you can see forecasting the temperatures in that column impacts what kind of weather precipitation type you're going to have. We just spent a lot of time talking about radar here, and the dual pole, the Doppler shift is used for detecting the speed of the motion of the particles. Yes, I can watch a particle move on radar reflectivity. I can see where the particles are moving. But here I'm actually seeing the actual motion of the individual particles. And maybe I'm real curious as to see why particles might be moving in a rotation. That may lead to a tornado forecast for me. Or maybe I can see the wind direction and see which way the wind are changing with height. By knowing that, I might be able to determine, oh, the forecast is going great, or no, it's not going so great. So all these parts are part of what you're seeing. We can use them for looking into tornadoes to develop as a hurricane comes ashore, or we can even see the wind, and we can calculate the amount of precipitation that fell. Dual pole is great for calculating the amounts of precipitation, which is a big plus. Phased array radar, we're never going to see it, at least not in my lifetime, because it's too expensive. It costs several $billions for each one. They're great because you can see the whole column of the atmosphere instantaneously. I got to play with one for about a week in Norman, Oklahoma at a thing where we were doing some training. It was fun to be able to watch a tornado form or hail develop in them because I could see it instantly and literally be able to make a forecast minutes before conventional radar would let me. We have different cloud classifications. We're going to talk about clouds this week, so look at them. Cirrus, high, thin, wispy clouds, they're all ice. Stratiform are layers, cumuliform are clumps. So hope you got a little bit out of this, and please don't hesitate to ask if you have any questions.